Modern front forks are incredibly adaptable, and since you can adjust pretty much everything, it can be intimidating to tune them at home. Also, it's really hard to understand how those adjustments translate onto the trails. In this episode, I'll explain you what's inside front forks, how they work, and how these adjustments can affect the performance. Most modern front forks that are performance-oriented have been following the same type of construction for the last 20 to 30 years. Inside, they have something called a cartridge, and you have open cartridge and closed cartridge forks. In this video, I'll use an open cartridge fork, which is easier to explain you how it works. On the outside of the front forks, you have the outer tube and the inner tube, usually made of chromed steel. If you take it apart, you'll find the push rod, which is a simple extension from the clicker on top to the rebound base valve. The preload spacer, which is responsible for setting the sag of the front forks. And the spring. And below the spring is where the magic happens. So let's see what's underneath all of this. So this is the actual cartridge where the damping occurs, thanks to two really special components that are placed inside it, called the valves, also known as pistons. And this is one of them. There is a fixed piston with orifices positioned at the bottom, called the compression base valve, which is responsible for the compression damping. Then, there is another piston with orifices that slides inside the cartridge according to the compression and extension of the suspension, called the rebound base valve. This piston also has the mid-speed valve, responsible for the mid-speed compression damping, but we'll talk more about this valve on another episode. These valves are quite simple, but they can be tuned in endless ways. Let's take a look at the compression valve. This valve is composed of a valve body, which is a metal disc with a center hole and outer holes, where the oil goes through and is attached to an aluminium body. Through the center of the piston, the oil flows with a variable restriction determined by the position of a needle, which is responsible for the low-speed damping, and its adjustment comes from the well-known clickers. The valve is obviously not made of the valve's body alone. On one side you have a check valve, which is a simple washer with a spring that allows the oil to flow in one direction. On the other side you have the shim stack, which is composed of different size shims, in diameter, thickness and material. Although the most common setup is a tapered double-stage shim stack, we'll use a tapered single-stage shim stack to keep things simple for now. Each valve creates damping at two different rates: low-speed damping and high-speed damping. Low-speed damping happens when the suspension is slowly compressed, and high-speed damping occurs when the suspension is quickly compressed. People usually associate these two damping rates to the speed you're going on the bike or how much the suspension gets compressed. But both hypotheses are incorrect. You'll understand this better later. So how exactly do the valves create damping? I'll consider three different chambers, one above the rebound base valve called A, one between the rebound and compression base valves called B, and another one from under the compression base valve to the outside of the cartridge, which I'll call C. Let's understand the low-speed damping first. Imagine the suspension being compressed, which means the piston rod slides down the cartridge. While this happens, the same volume of oil is pushed outside of it, through the compression base valve. The oil flows through the low-speed compression orifice, which restricts the oil's flow and creates low-speed compression damping. In the meantime, the check valve in the rebound base valve opens to fill chamber A with oil, without creating any considerable damping. When the suspension reaches its lowest point of compression, it rapidly starts coming up due to the spring's force. The volume of oil that is in chamber A is forced to go through the low-speed rebound orifice in the rebound base valve, restricting the oil's flow and creating low-speed rebound damping. As in the compression stroke, the check valve opens in the compression base valve to refill the cartridge without creating any considerable damping.
This dance between check valves and low-speed orifice doesn't happen step by step as I explained. It's a rather simultaneous process, but this gives you already a good idea on how it works. Let's see what happens when you compress the forks faster and deeper into the stroke.
While they're compressing, the same volume of oil as the volume of the piston rod entering the cartridge is pushed through the compression base valve. The oil is forced to flow through the low-speed compression orifice, restricting the oil's flow. The check valve in the rebound base valve opens, allowing chamber A to get filled with oil. However, there is not enough oil going through the low-speed compression orifice to prevent the oil pressure to build in the cartridge, especially in chamber B. The pressure keeps rising until it's high enough to bend the shim stack, allowing more oil to exit the cartridge. The shim stack is continually resisting the bending due to its leaf spring effect. The more the shims bend, the more the high-speed valve opens. And the bigger the pressure in B, the more oil can go through the valve and the less damping you have.
This might seem counterintuitive, but the resistance to oil flow is good to a certain degree. If there is too much damping, the suspensions will feel too harsh and won't be able to soak up the bumps.
When the suspension reaches its lowest point of compression, the spring makes sure it extends again. Since this time we compressed more deeply, the spring makes the outer tube extend faster. The piston rod slides up the cartridge, and the volume of oil that is in chamber A is forced to go through the low-speed rebound orifice, restricting the oil's flow. The check valve in the compression valve opens, allowing the cartridge to get refilled. Like in the compression stroke, there is not enough oil going through the low-speed rebound orifice to prevent the oil pressure to build in chamber A. The shims on the rebound base valve bend, allowing more oil to flow between chambers and reducing damping. When the pressure in A decreases to a point where the bending forces of the shim stack is greater than the oil pressure exerted on it, the valve closes and the oil only flows through the low-speed rebound orifice and check valve.
As you could see, both low-speed and high-speed damping take place at the same time. This means that any change on the low-speed damping will affect the performance of the forks during high-speed damping. The precise moment when the high-speed damping valves open can be completely tunable, and that's why it's such a complex art. But let me clarify something. You can have high-speed compression damping, but not high-speed rebound damping in comparison to what I just showed you.
If you're riding on a single track and you hit a nasty tree root, you will have high-speed compression damping, since the compression is quite fast, but because the forks weren't compressed that much, you won't have high-speed rebound damping. And on the other hand, you can have high-speed rebound damping without having high-speed compression damping, like when you're braking on a downhill or on G-out sections. Remember the needle restricting the oil passage on the low-speed orifices? The position of the needle is adjusted by the clickers, and it's actually just a bolt with a needle on the tip. How much the needle blocks the low-speed orifice depends on how much you tighten the clicker. If you fully unscrew the clicker, the needle will restrict the oil flow the least possible, creating the least amount of low-speed damping on a fork and delaying to a small degree the high-speed damping transition created by the shim stack. If you fully screw the clicker, the needle will restrict the oil flow the most it can, creating the biggest amount of low-speed damping on the fork and anticipating to a small degree the high-speed damping transition created by the shim stack.
What about changing high-speed damping? On front forks, you have to fully disassemble the forks and the valves. Although the clickers change and affect the high-speed damping to a certain degree, this is where suspension workshops come in. The way you stack the different kind of shims is what will originate the bending forces that will make the valve open or close according to the pressure between chambers.